Good morning and welcome to Tech 259 on Monday, April 26th. In this first video, we're going to review problem set number 17 about batteries that we talked about last time. And in the second video today, we'll continue our discussion of energy storage to talk about a couple different kinds of energy storage. But first, let's go over problem set number 17. So to do that, I will share my screen. So now you should see problem set number 17. Problem number 1 said that we had a battery bank of 24 lithium iron phosphate cells connected in series. This is actually exactly what my motorcycle battery bank is. It actually has 24 cells of lithium iron phosphate batteries. When lithium iron phosphate batteries are fully charged, each one has a voltage of 3.4 volts. And when it's essentially fully dead, it gets down to about 2.5 volts. So when it's fully charged, it's at about 3.4 volts. When it's basically dead, it's at about 2.5 volts. There's very little energy left in the battery when the cell voltage is 2.5 volts. All right, so A says, what is the voltage of the battery bank when it is fully charged? When it's fully charged, each cell in the battery bank is 3.4 volts, and they're in series. And we know that when things are wired in series, whether it's a solar cell wired together in series to make a solar panel, or whether it's a battery cell wired in series to make a battery bank, we know that the voltages add. The voltages add when we have things wired in series. So what we're going to have here is 3.4 volts plus 3.4 plus 3.4, 24 times, or 3.4 volts times 24. So here is what we got right here. Here's our battery bank. There's 24 of these individual cells wired in series. We know the voltages add when they're in series. So we have 24 cells times 3.4 volts per cell. Cells cancel out, and we get 81.6 volts. And I can tell you from experience, that's right about the voltage of the battery pack on my motorcycle when it's fully charged. Part B is very similar. It just says, what's the voltage of the battery bank when its cells have been essentially fully depleted? So when it's fully depleted, each cell is going to have a voltage of about 2.5 volts. So now we just take 24 cells times 2.5 volts per cell, and we get a battery bank voltage of 60 volts. All right, so certainly the voltage of the battery bank drops as you're depleting it. You know, as I'm riding along in my motorcycle, the voltage drops. However, like we talked about last week, the voltage is not a good indicator of the state of charge, because what's going to happen, it's going to drop down from 3.4 volts to about 3.2 volts real quickly. You know, by about 95% state of charge, it's going to be about 3.2, 3.25 volts per cell, something like that. But it's going to stay right there at around 3.2 volts, you know, between 3.1 and 3.25. It's going to stay there all the way until its, you know, state of charge is maybe like 30%, something like that. So just knowing that the voltage of each cell is 3.2 volts does not give you a good indication of the state of charge of the entire battery bank. So that's why, like we talked about last time, you need to actually measure the amount of energy coming in or out of the battery when you're charging it or discharging it, respectively. Part C says that each cell has a capacity of 60 amp hours. Remember, we talked about amp hours, how that's how the capacity of batteries is usually measured. It itself is not directly a unit of energy, but you can convert into energy pretty easily by multiplying times the nominal voltage. What is the energy storage capacity of the battery bank expressed in kilowatt hours? Assume the battery cells have a nominal or average voltage of 3.2 volts. The nominal voltage just makes the math easier for us. So the easiest way, there's different ways to do this. I'll show you a couple different ways. The easiest way is just to say, all right, if the nominal voltage of one cell is 3.2 volts, then the nominal voltage of the battery bank is 3.2 times 24, which is 76.8 volts. And then the battery bank has 60 amp hours. Remember, when they're wired in series, like they are, the currents do not add. The voltages add. When you have things wired in series, the voltages add, the current stays the same. When you have things wired in parallel, the voltage of the system stays the same and the currents add. So in this case, we added the voltages to get that voltage for the battery bank, but the current stays the same. So it's still capable of providing 60 amp hours, but the battery bank is capable of providing 60 amp hours at 76.8 volts. So all we got to do really is take 76.8 volts times 60 amp hours. When you take amps times volts, you get watts. And we've got hours in there as well. So when you take volts times amp hours, you get watt hours. So our answer is 4,608 watt hours, or 4.608 kilowatt hours, right? Because it asks for it in kilowatt hours. So if that makes sense to you, the way I just explained it, then by all means, do it that way. I did it a little bit differently to break it down into some more steps when I calculated it here. So here I said, let's suppose each cell individually provided 60 amps at its nominal cell voltage of 3.2 volts for 1 hour. If it did, then the power that it would be providing for that hour is 60 amps times 3.2 volts, which means it's going to provide 192 watts for 1 hour. And now we can say that we can calculate the energy for that cell because it provided 192 watts for 1 hour. And we know that energy is power times time. So take 192 watts times 1 hour, and you get that the energy storage of each cell is 192 watt hours per cell. But we know there's 24 of them. And so we can take that energy capacity per cell, take that times 24 cells, the cells cancel out, and you get the same answer as we did before, 4,608 watt hours, but it asks for it in kilowatt hours. So do your conversion here. 1 kilowatt hour is 1,000 watt hours cancel out, and you get 4.608 kilowatt hours. All right, that's it for number one. Number two says, well, it's a little explanation of the C rate that we talked about last time. And the question says that we have a lead acid car battery. It has a nominal voltage of 12.0 volts and a capacity of 100 amp hours. Those are both realistic numbers for a car battery. A says, what is the energy storage capacity of the battery expressed in kilowatt hours? So this is just like part C. There's pretty much the exact same thing. So we've got a 12 volt battery. It's rated at 100 amp hours. Let's suppose it provided 100 amps at 12 volts for 1 hour. Then we can calculate the power. It's equal to current times voltage. 100 amps times 12 volts is 1,200 watts. And it's going to do that for 1 hour. It's capable of doing that for 1 hour. So we can use our energy calculation. Energy is power times time. 1,200 watts times 1 hour gives you, well, I did the conversion here. So 1,200 watts times 1 hour would be 1,200 watt hours. But I went ahead and did the conversion here. I canceled out watt hours and I got 1.2 kilowatt hours. All right. There's another way to do this that's easier if you're comfortable with it. If you just want, you can take 12 volts directly times 100 amp hours and recognize that volts times amp hours gives you watt hours. So you can just directly take 12 times 100, you get 1,200 watt hours, and then divide by 1,000 to get into kilowatt hours. Okay, and then letter B says, if the battery is discharged at a constant rate of 22 amps, what is the C rate? So here you have to use the equation that we talked about to calculate C rates. Remember, C rates are a way to non-dimensionalize the charging or discharge rate so that we can make comparisons between small batteries and large batteries in their charging and discharge rates. So it is commonly used in industry. You'll definitely hear about C rates being used to measure charge and discharge rates. So here's our equation for the C rate. It's equal to the current that's being drawn or being used to charge the battery at that time times 1 hour divided by the rated capacity of the battery in amp hours. So in this one, it says it is discharged at a constant rate of 22 amps. So that's going to be right there for our current. And we know that it has a capacity of 100 amp hours right here. So all we got to do is plug in those numbers. 22 amp hours divided by 100 amp hours gives you 0.22 C is the answer here. So the C rate for this situation is 0.22 C, which is a pretty low discharge rate. That's not going to damage the battery any more than necessary. I mean, every time you charge and discharge the battery, it degrades the battery a little bit. But if you charge it or discharge it really quickly, you know, at like 5C or 8C or something like that, you're going to damage it more quickly. So that's a pretty low discharge rate. Remember, we talked about anything less than 3C is a fairly low discharge rate. All right, letter C is if the battery is discharged at a constant rate of 3.2 C, what is the current flow in amps? So we use that equation again, and this time we know what the C rate is, and we know what the capacity is, and we're trying to find the current. So we just use our same equation. We plug in 3.2 for the C rate, and our capacity is 100 amp hours. And then you just solve for the numerator here. So you're going to take both sides times 100 amp hours, and then divide both sides by 1 hour right here. And then you're going to get 320 amps. So that's a pretty high discharge rate. I mean, that's a lot of current. A discharge rate of 3.2 C is a pretty high discharge rate. If you do that very often, you're going to shorten the life of the battery. All right, that's it for problem set number 17. As always, let me know if you have any questions. And in the next presentation, we will start talking about some different kinds of energy storage. So I'll see you in the next video.